So do you have any idea about how the proof possible? I haven't seen the proof, but I don't have any idea how to prove it.
Proof of what?
Oh, that fifth polynomials has doesn't should means how to connect with the S5.
Quintix can't be
Okay, I'll
solved with
maybe
that.
give you a I mean, I'll try and find an exposition. I mean, there's a pretty nice exposition. So at least that's the one proof that I sort of know very well using commutator. I can tell you more about it at a later point. Okay, so let's start. So this is going to be lecture 9, but I mean, it's part 2. So we are going to start part 2. And this part is going to deal with, I mean, this is what we want to do. We want to do computations on polynomials. But in the course of it, we might have to learn a little bit about these objects that are called rings and fields. But I'm going to keep deferring properties of these things until we need them. So because rather than just bombarding you with various sorts of definitions and properties and so on, I'm going to keep things as basic as possible, but every once in a while we will start needing certain kinds of things, and then we'll have to specifically look at the definitions and state it in the right form of generality and so on. Okay, so far we've been dealing with groups where it was basically an underlying set which had a single operation, which we just call star, but sometimes mentally it was addition, sometimes it was multiplication, sometimes it was composition, whatever. And the thing is, since we always dealt with the groups as being bijections or something, the elements had turned out to be bijections. I mean, you're hopefully used to the fact that groups, the operation on groups need not be commutative, in the sense that the order matters. I mean, A star B need not be equal to B star A. So usually they're not assumed to be commutative, but now we'll be dealing, most of the groups that we'll now start encountering will be things where, I mean, it basically is going to be addition or multiplication. So they naturally commute with each other. Okay. So in this class, we're going to, this part of the course, we're going to deal with polynomials, which are groups, because in some sense, there is a zero polynomial, which is like the identity element. And you can add two polynomials and subtract two polynomials. So the set of polynomials under addition certainly forms a group in the way you are used to. But the point is, it does more than that. The sense that you also now know, you have a notion of multiplying two polynomials. So it's like a group with some extra structure on top of it. And it will turn out that this forms a different sort of object, which is called a ring. Okay, but don't worry about it right now. We'll deal with it when we get there. Okay. And then in this part of the course, we are basically going to be interested in a whole bunch of tasks related to these polynomials. And we will see examples where these sort of computations on polynomials sort of show up naturally in problems that don't particularly seem to depend on polynomials at all. It's just one of these intermediate steps that you go through. So it's very natural that sometimes you might just want to do operations on polynomials in a reasonably efficient manner. Okay, so what is a polynomial? Well, a polynomial is an expression of this sort. I'm not going to formally write down a definition, because this is one of these things where you see it and you know it, right? But we'll deal with those things, exactly what a ring of polynomials is, etc., at a later point. But basically, they are expressions of this form where you have some formal variables. In this case, there is a single variable x. Okay, and it's like a formal sum of the form each monomial, which is like a power of these x or a product of these formal variables, comes with a certain coefficient, and then you add them up. Okay, and these coefficients usually come from a certain world. There is a certain space of coefficients that it comes from, which is called a field or whatever. But the point is, basically a polynomial there's a bunch of coefficients, and for each monomial that is present in the polynomial. And what are the sort of operations we might want to do on them? So here are some list of things that I've just written down, and many of them are things that you would see in part 2 of the course. So the first and the most basic thing you could ask for is, can you do the basic operations on polynomials, which is to maybe add them or multiply them or divide them if it makes sense, etc. And you can, of course, be a bit more sophisticated about divide, in the sense that, can you do something like the division algorithm? where you get the quotient and the remainder and stuff. So these are some operations, and of course we would want to do this quickly. Okay. And maybe, I mean, maybe a little more advanced things is like, can you somehow factorize them into prime factors? So on the face of it, it's unclear what prime means here. And it's also unclear when we say we factorize them, is there some notion of uniqueness that's going to happen and stuff like that? So those may be some questions that we may have to deal with at a later point. Or maybe something else that you care about is like, I give you a polynomial and I give you a bunch of points. I give you many points. Can you evaluate this polynomial on all these points quickly? Okay, so this is like the polynomial evaluation question. And in fact, the way I phrased it, it's like the multi-point evaluation question. I want to simultaneously evaluate it on many points. Or maybe you're interested in questions where I give you a polynomial and you're interested in finding its roots. Again, whatever that means. Okay. And though all of them seem to be like statements about polynomials over a single variable, maybe some of them make sense, even if there are polynomials over multiple variables. Okay, so often we might have to get a sense of, does this make sense? Are these questions meaningful? Are answers something that we can hope to compute quickly? So those are things like, for example, the notion of roots seem unclear when you're talking about multivariate stuff and so on. So we might have to appropriately modify the questions that we are asking. Okay, so the way I'm going to proceed with this is like, I'm going to start off with some of the most basic operations you could think of on polynomials. And I'm going to do it in a way where I'm hoping that every time we do something, we get drawn into a different sub question. And we try to deal with that sub question, maybe learn some properties, and then come back to this thing of, okay, what other tasks can we do? So that's going to be the rough setup. But in some sense, if you want to look at where are we eventually going to go to, like what's in some sense the coolest application that you're going to learn at the end, it's actually going to be to factorize polynomials. Okay, and we will see some algorithms to factorize polynomials, which are amazing. I mean, on the face of it, it feels like this must be a very, very hard problem, but it will turn out that these are things that we can do efficiently. Okay, so yeah, so for now, I'm going to deal with polynomials in one variable, and it's often referred to by this notation fx, though this will become clear soon enough as to why this notation means. Just think of it as like, this is the place from which your coefficients come from. And this just indicates that you're looking at polynomials in one variable. Like, for example, if you're thinking of polynomials in a single variable x, where all coefficients are real numbers, then you will think of that as Rx. Okay. Or maybe you're interested in polynomials where all coefficients are, let's say, integers. Then you might think of it as Zx. Okay, so that's usually what it means. And in fact, for now, I'm going to assume that Zx is not something that I'm going to be interested in. I'm going to be interested in these things f, which form what is called a field, though we will expand our horizon soon. For now, I'm going to assume that this is a field. Okay, what the hell is a field? A field is basically your notion of what numbers are typically. Like, it's something in which you can add stuff, you can multiply stuff, and everything other than 0 has an inverse. Like, there's a 1 by x for everything other than the 0. So formally speaking, a field is some underlying set along with two operations, which is multiplication and addition, such that if you just think of the field under addition, it forms an abelian group. That just means that you can add two elements and you can subtract two elements. The notion of subtraction makes sense. And the identity element under the addition operation is referred to as 0. Okay. And the extra thing is also that the property that's this multiplication satisfies is that if you remove the 0 element and look at the rest of your elements in the field, then that also forms an abelian group under the multiplication operation. That is, for every a, there is some other b such that ab equals 1. There's a notion of 1 by a and stuff like that. This just means that you can divide. Okay. And the identity element in this operation is called 1. And you have this notion that multiplication distributes over addition. So A times B plus C equals, I mean, AB is just shorthand for A times B. So AB plus C. Basically, whatever we are familiar with, we are just giving it a name. Okay, so that is what a field is, and we will, in at least for today's lecture, we will assume that the coefficients are coming from some field. Like I have a way of dividing by whatever coefficient I see. Okay, and here are just some examples, okay, which are things that should be familiar to you. One is the field of rational numbers. I mean, just observe that all the rational numbers certainly satisfy all the axioms that I have listed above. And then there's also the field of real numbers and the field of complex numbers, etc. But there are some slightly more perverse fields which take a little bit more time to convince yourself that this is actually a field. So I'll just give you a few examples so that you keep these things in mind. Not everything may be as nice as rationals or reals or complex. So for example, here is an example, which is the set of all elements of the form a plus b root 2, where a and b belong to the rational numbers. Okay. One thing that is easy to see is that certainly if I add two numbers of this form, I get another number of the form a plus b root 2. Similarly, if you multiply two numbers of this form, you will get a number of this form. I mean, the root 2 squared becomes a 2, so you can absorb it into the a part. What is unclear is why does division of two such numbers, why is that of a number of the same form? But hopefully these are things you have done in high school, right? You will multiply with a minus b root 2 and do some stuff like that. So, but turns out that this is also a field because it satisfies all the axioms that I mentioned above. And here's a slightly more bizarre example. So this is all like rational expressions of the form f of x by g of x, where both f and g are polynomials from your, I don't know, from your favorite place, with g not equal to 0. Okay. And with a suitable notion of what equality means, what addition means, etc. These are all, I mean, you should know. I mean, there's only one definition that sort of makes sense types. Right. So this also happens to be a field. And then there are these other strange classes of fields, which is made up of, let's say, elements of the form 1, 2, 3, 4, 5, and 6. Okay. And by that, what you mean is you add numbers mod 7 and you multiply numbers mod 7. And hopefully you've seen in your MFCS course or some other course that, this also satisfies all the axioms that we want. But this is again, so these things are called finite fields for an obvious reason, because they are finite in size. Okay, and finite fields is something that we will deal with soon. But I'm just at the moment just giving you some examples for them. So the point I'm trying to also make here is that when we are talking about many of these tasks, I mean, it's natural that many of these tasks depend on where your coefficients come from. So when we say that I want to do something quickly, like what does that mean? Okay, there's some running time, but the running time is not just a statement about manipulating things. It's also about dealing with the coefficients that you end up seeing, right? So for instance, at the moment, it doesn't even make sense to sort of ask, what is the input size, for instance? One of the coefficients turns out to be a pi. Okay, so it just feels like, what am I supposed to do here? I mean, like, there is suddenly this weird bit complexity, etc., that seems to be going in. So at this point, what I'm going to just assume is that we will make the following model assumption on these computational tasks, which is that we will just abstract out the fact that there are these coefficients. Let's just assume that there is some unit cost operation to add stuff or multiply stuff or divide stuff in the underlying field. Like whenever we are manipulating coefficients, let's just assume that if you are interested and I give you some particular field element and I ask you what is the inverse of this element, we'll assume that we get it for free. Like that is like a constant time operation. The only thing we are going to try and count is how many non-field operations do you need to accomplish the task that you're interested in. This is the way of just abstracting out where the coefficients are coming from. And let's just say that somebody provides us a library to do arithmetic in that domain. Okay, so let's ignore those sort of weird technicalities and focus on the more interesting task, which is eventually I want to deal with polynomials, what do these computational tasks on polynomials cost me? Okay, but as we proceed further and further, we might start paying attention to how much time it takes in order to even manipulate things at the coefficient level. But for now, I'm just going to assume that we'll just count any multiplication involving two rational numbers or two real numbers. I'm going to count that as a unit time operation. But on the other hand, if you want to multiply, x squared plus 4x plus 5 times 3x squared plus 5x plus 7, there I will count how many field operations did you need to do in order to compute the final answer. So I'm only going to count the number of field operations. So I hope this sort of simplification seems reasonable at this point. It's just to abstract out the fact that fields could be ugly. I don't exactly know what the underlying operation there is going to be. And for the moment, I'm going to ignore it. Okay, so good. So we're going to start with the most basic of operations, which is I give you two polynomials f and g. Okay, and I want you to compute what f plus g is. Okay, so I need to be a bit precise here and say, what do I mean by given? And what do I mean by compute? Okay, and again, for now, we will assume the most natural way of of saying this, which is that both of them, I'm going to say I want it as a list of coefficients. Okay, so think of it as an array that is provided to me. That's what the input looks like. The array is going to basically say, by the way, this is the coefficient of x naught, x bar 0, x bar 1, x bar 2, blah, 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 till x bar d. I'm given something like that for f and something like that for g, and I'm expected to return something like that for f plus g. Okay, so this is the model that we are currently interested in. Maybe at a later point, we might be interested in polynomials given as circuits or whatever, if you want to get fancy. But we'll get there when we get there. But at the moment, everything, we are just given a list of things, list of coefficients, and we want to do computations on the list of coefficients. So,
hey, sorry, just
yeah,
a silly thing. You've written about you only want to count the number of non-field operations. Did you only want to count the number of field operations?
Oh, okay. Actually, I should have. Okay, so what I meant to say here was.
Yeah, I mean, I got
yeah.
you're trying to say.
Or rather, okay, what I should have said, the number of field operations required to compute one non-field
operation. Sure.
Yeah, mostly we are going to be interested in some non-field operation. Like, for example, f plus g is like one non-field operation because it's an operation on the polynomial place. And I instead want to say, if I'm only allowed to do field operations for unit cost, how many field operations is going to take? Yeah, so it's right. Yeah, I should have written it properly. Okay, so I'm just going to be
clear for me actually. Can you just
sorry?
So I didn't clearly distinguish between field operation and non-field operation.
So let's just do one example. So basically, the thing is, one can say that if I'm interested, I give you an f, I give you a g. I ask you to compute f plus g. It's like I'm asking you to compute one operation, which is addition of two polynomials. But in order to do that, you might have to do many coefficient additions. So what I want to count is, in order to compute one such polynomial operation, how many field operations did you actually need to do this? Okay, so maybe let's just look at an example.
How many additions or multiplications you are doing?
Yeah, exactly. So every time you give me two. Just imagine thinking that somebody has given you a library where you can provide it two numbers and say you want to add it or subtract it or multiply it or divide it or something. And at unit cost, it will tell you, by the way, this is the answer or something like that. Okay, but if that's all you're provided, but now I instead give you two polynomials and I ask you to add them, how much time would you take? Those are the sort of questions we will be interested in. We are not going to worry about how much time the library took to do those computations. For the moment, we are going to completely ignore that. Okay. Now this is like, I'm just going to state it because this is like utterly obvious, which is, let's just think of it as this is the coefficients that are provided for f. So this just means that this is the coefficient of x bar 0, then it's the coefficient of x bar 1, blah, 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 blah. This is the coefficient of x power d. Normally, I might end up mixing up notation. I will assume that degree of f or degree of G, this is like at most D. So the input size in some sense is an array of something like D elements. Again, some of these coefficients could be pi and E and whatnot. It's just that at this point, we're not going to worry about it. It's like, I'm given a list of D elements or D plus 1 elements in this case. Okay. So, and similarly, I have G, which is an array like this. Okay. And what should F plus G be? I mean, you just build an array where this guy is going to be this plus this. Similarly, this guy is going to be this plus this or whatever. I mean, you just add component wise. Okay, and that's it. So that's what this is. So this basically says the time complexity is basically equal to D plus 1. The number of invocations of this library was D plus 1 because I made one call for adding these two numbers, one call for adding these two numbers, etc., and one call for adding these two numbers. Okay, and we will just, I'll soon start becoming very sloppy, so I'm just going to write this as order B. I mean, it's linear in the lengths of the input. Okay, again, I'm just ignoring the fact that there are coefficients involved. Coefficients could have large bit sizes and so on. We are just ignoring all those technicalities. But as we progress further, we might pay attention to that. But for now, let's just not worry about this. Okay, and now let's do the next thing, which is the next silliest example, which is to compute polynomial multiplication. Okay, so now the task is again very simple. You are given f and g, again given as a list of coefficients, and you are told that the degree is at most d. Let's say that's an upper bound that we have. And now I want to compute the polynomial fg. Okay, and I want to know how many field operations would it take. Okay. Now, in all these things, you should always start off with the stupidest algorithm and then see if you can keep improving. That's what we're going to do here. I mean, some of you may have just seen the best possible algorithm for this already in other contexts, but I'm going to take a slightly winding route because in the process, we'll discover some new techniques for that. Okay, so let's just write down explicitly, what is this polynomial h going to be? Okay. So this h of x, this is just going to be summation, let's say I going from 0 to, the degree can be as large as 2d. Okay, and I want to know what is the coefficient of x power I, and what should I write here?
This convolution thing.
Right, so this will basically be something like from j going from 0 to d, fj gi minus j or something. Okay, so this is just an expression, and once you have an expression of this sort, this naturally leads an algorithm. Let's literally just compute everything that is here. Okay, so for each such I need to, what all do I need to figure out? I need to compute all of these products for every j and then add up all of them. So it looks like there are something like d multiplications and d additions in order to compute one such coefficient. And I might have to do this for roughly like 2d such coefficients. Not all the coefficients are of the, oh, sorry, I think this must have been I. Yeah. Okay, not all the coefficients are going to take just as much time. Like, for example, the constant term is just f0, g0. But the degree 1 term has two such things, and it becomes larger and larger. But if you just look at how many total operations did you do, okay, so you get that the time complexity here, this is like order d squared. Okay, this is like the standard high school way of multiplying numbers or multiplying polynomials, etc., etc. So obviously, what we are going to be interested in is, can we do better? Okay, so is d squared really the best possible algorithm we could come up with, or can we come up with a better algorithm? Okay, Yeah, it's one of these things where if I ask people for ideas or something, there's a possibility that you might just jump straight ahead. So I'm going to instead tell you what I'm looking for, and then we will do that. Okay. So what we are going to do is we are going to try and do some sort of a like an induction type argument or some way of doing some divide and conquer, like CS people. I mean, you should try and break your problem into sub problems and solve those sub problems and somehow figure out what's happening. So what I'm going to do instead is the following. I'm going to say, this was my F that was provided to me, and this was the G that was provided to me. I'm going to think of it as breaking it in the middle. Okay, where this is the left half and this is the right half. I mean, I'm thinking of this as the lower degree terms and then the higher degree terms or whatever. Okay, and these are the lower degree terms and the higher degree terms. So if you think about it, like, what does it mean? Like, for example, if I just think of just the left half alone, that also looks like a representation of a polynomial, right? And whatever that polynomial is, let's just call that F low. Okay. And if I look at the right half alone, that also looks like a polynomial because that is like a list of coefficients. So I'm going to call that polynomial as F high. Okay. So how does the old polynomial relate to F low and F high? So it's basically of the form, it's this plus x power d by 2 times F high, because you need to shift it by, I mean, F high is like saying that this is like the constant term, but it's not quite the constant term. It's the coefficient of x power d by 2. Right. And similarly, I have a polynomial of the form g low and x power d by 2 times g high. Okay. So let's instead ask the following. Suppose you magically had some way of computing products of degree d by 2 degree polynomials, because notice that all these 4 polynomials are all polynomials of degree d by 2. Their degree has halved in some sense. And if I know how to multiply them or something, can I use that in some sense to compute the final product? Okay, so let's look at that. So what is H going to be? H is going to be equal to F low and G low plus F low times G high plus F high times G low times x power d by 2 plus F high G high times x power d.
It is only true for the, you can do for the even degree, right?
I mean, okay, I mean, by d by 2, I just mean just choose the integer that is.
If it is a odd degree, you can just take a 0 into even degree to make it higher and do it.
I mean, you could, but you just break. I mean, all I mean is it's not particularly important that it is right in the middle. I mean, I just want the 2 sub problems to be substantially smaller than what I started off with. So you break ties. I mean, like, if you're working with a degree 7 thing, maybe put, I don't know, degree 3 here and degree 4 here or something. I don't think it makes too much of a difference.
You are telling us in this way, we will reduce the number of operations also.
Yeah. So, but we need to convince ourselves. We still haven't done anything so far. I've just written down some expression. I want to know if, are we coming up with a weird way of touching our nose steps, right? So, okay, let's look at this. So suppose T of D was the time that it was going to take to compute a degree D polynomial. Okay, now I can basically say, okay, let's compute this product recursively and this product recursively, this product recursively, and this product recursively. These are all polynomials of degree d by 2. So let's compute all of those products. Okay. So what is the recurrence going to be? So I have 4 such polynomial multiplications of degree d by 2. Okay. And after I do that, what else do I need to do? I am also expected to add a bunch of things. Right. So this is going to end up being some whatever degree d polynomial. This is another degree d polynomial. So I might have to add them up. Okay. So all that thing might take an additional order d operations. Okay. So I hope this is clear, because each of these are polynomials of degree d by 2. So I'm recursively calling the polynomial multiplication algorithm. And I have 4 such recursive calls. That's why it's 4 times d by 2. Plus this is this intermediate whatever extra that I need to do. In order to, once I get the answers, I might have to do something. Right? Or even to break this up into f low and f high, I might have spent some order d time or whatever. Okay. And if you look at all of this, you basically, if you solve this recurrence, you get order d squared. Okay. Which was something that we could do anyway. So it seems like, on the face of it, we are not really making progress. Okay. But this insight turns out to be very, very useful because Anatoly Karatsuba, I think this was in the 60 probably. I think it was in the year 60, or maybe it was published a little later or something like that. So showed that you can actually you can improve on top of this by being a little more clever. Okay, which is, so it's a sort of miraculous thing. I mean, if you have seen this becomes obvious to you, but I think the first time you encounter this is like, oh wow, I mean, how did someone think of this? So what Karatsuba suggested was that let's instead compute the following products. Okay, I need f low g low. Okay, and I need f high g high. Okay, and I'm going to compute the following thing: f low plus f high times g low plus g high. Okay, these are the only 3 things I'm going to compute. Okay, let's give this names. Let's call this A, and let's call this B, and let's call this C. Okay, and now, okay, what can I say about h of x? I mean, so this is going to be A because that was what was f low g low, which I already have. That's my A. Okay, and then there is a whatever b times x power d, which is just a shifted version of what the polynomial b was. And the cool part is the following, which is that this is exactly c minus a minus b. Okay, because just notice that what is this expression? It's like f low g low. I mean, there are the corner terms and there are the cross terms. The cross terms are what you want. You want f low g high times f high g low. But the corner terms you already have access to. So if you subtract that off, you're now left with exactly what the cross terms are. Okay. So now let's look at how much operation does all of this take if we were to do this. So we first compute these sums, f low plus g low, f high plus g high. That takes some d steps. Okay. Once we compute these sums, we recursively call these 3 products. And once we compute the 3 products, we then do some subtraction. That's another d steps. Okay. So overall, what is the recurrence going to be? This t of d is going to be 3 times t of d by 2, because that's the number of operations you need. I need to compute this product, and this product. And technically speaking, I should have written it this way. Okay, there is an order d operation in order to compute f low plus f high and g low plus g high. Then there are 3 recursive calls to multiplication. And then there is another order d operation in order to compute c minus a minus b. Okay, so this is the recurrence, which is you're now going to get, it's going to be equal to order d plus 3 times d over 2, t d over 2 plus order d again. Okay, and what do you get when you solve this recurrence? So, I mean, you can try this out, and so you end up something like this is log 3 by log 2, or log 3 base log 2. Okay, and this is roughly equal to I think this is like 1.584 something. Okay, which is substantially better than order d squared, which is what we saw in the naive high school method. And this was Karatsuba's algorithm. It's a very simple divide and conquer algorithm. And this is from the 60s. The 60s that basically tells us that you can do polynomial multiplication in sub-quadratic time. Okay. Yeah, but we shouldn't be satisfied with this. So we should ask, okay, can we improve on this?
Oh, before that.
Yeah,
So,
yeah.
I mean, this is like still divide and conquer, but just with some clever computation, you could get from just d square again to d1.5.
Mhm.
Is there some way to say divide and conquer can't give you better than this?
I mean, you will see why when we figure out how to improve on this idea.
Okay.
I mean, like we will see a divide and conquer type algorithm, but a little more clever than that, which will improve on this idea.
Oh wait, okay. I think I just realized that the algorithm that I know of, maybe that is divide.
Yeah, that's already a divide and conquer. But
Okay.
let's sort of. I'm going to purposefully take a slightly long-winded route because it introduces some other principles. Okay, so I hope Karatsuba's algorithm is clear. It's one of the simplest algorithms you could think of, and it's pretty clever that you could come up with some weird products, and somehow those three products gives you the four terms that you're interested in. So rather than computing four naively, you could somehow get away with three with a few more additions. Basically, additions are cheap. So if you can trade off some of these polynomial multiplications for additions, you're making tremendous progress.
Oh,
Okay.
I think also something if someone hasn't seen this before, it's not just polynomial multiplication; it improves general multiplication time.
Yeah. So by the way, so in fact, Karatsuba's original motivation was to do integer multiplication, because integer multiplication you can think of as somebody gave you a polynomial where all the coefficients were zeros and ones, and you just evaluate the polynomial at the number 2, because that's what the binary representation is like. So the same idea just works there as well. There's nothing special about the fact that we are working with polynomials. Okay.
I have a follow-up question for that.
Yeah.
So how we can reduce the number of orders in the case of addition of two elements taken from rational functions?
Hold that thought, because one of the things that's unclear is like, how do you, because in order to add two rational functions, you already need to know how to do multiplication and stuff.
One can always do that if f1 by g1 plus f2 by g2 equals to g1 g2 f1 g1 f1 g2 plus g2 g1. That always,
so which already means that at the base of it, you need to compute those products.
Yeah, means in that way we are doing extra, because we are not exactly doing the LCM of g1 and g2 basically.
Yeah, so we'll get there soon, because we'll once we do polynomial multiplication and so on, we'll also see polynomial division, and it'll eventually turn out that there are all very efficient algorithms for this. So just hold this thought for maybe until the next lecture, when we see that algorithm completely, or maybe the lecture after that. But that time, that will probably tell you how to do the same thing for rational functions, etc. If you can do these basic operations well, okay, don't be satisfied with 1.58.
One more thing about the previous. So if I take the f to be r, the number of operations whatever we are getting, if you just take f to be c, it will get more, right?
Sorry, you mean this, right? Where the coefficients are coming from.
Yes.
Yeah. So which is why at the moment I am completely abstracting out how much time it takes to compute such product.
I am just so in C there are if you just see the multiplication of C or addition of C is as a one operation, but if we view as in R, it will be like four operations: a plus id plus b, c plus id, or means there are, if you see as a real operations field of R, then it will be more operations, right?
That is true. So again, hold that thought, because many times the reason why I sort of took this slightly different view, that we will assume this, and we will start paying attention to this, because many times what we might end up doing is the following. You want to do something on the reals, but you might artificially end up going to complex numbers because something else is present there, which is useful for you. But then you need to count things correctly. So at that point, we will start paying attention to, okay, fine, I only gave you a library to multiply real numbers. You can't now feed it complex numbers and ask for things in unit time. So you need to account for those. So those are things that we will do. For now, I'm just going to assume that, let's just assume that arithmetic on the underlying field is free. And by free, I just mean it's a unit cost operation. Okay. And so eventually I technically should be writing is that the time taken for this is order d squared times time for multiplying, doing arithmetic in the field. That's the real time taken for all of these things. I'm just ignoring this extra factor. Okay, so now I want to ask, okay, can we improve on this idea? Okay, so what did we do here? We said, okay, let's take our f and g, break it up into two chunks. And naively, it seemed like we needed 4 multiplications. We needed to figure out 4 terms. But we somehow got away with doing with just 3 terms.
Shall I propose something?
Yeah, go ahead.
Take the break f in odd degree and even, means coefficient of odds and even separately.
Okay.
Similarly, g, and do the same thing.
Yeah, so that again will tell you that you need odd terms and even terms. So you might again end up changing 4 operations into 3 operations. Something very similar will happen here. I mean, unless I don't know if you're going to where I think you're going, but okay. So let's do the next I don't know, knee-jerk reaction to these things, which is okay. We broke it up into 2 parts. Okay, can I instead break it up into 3 parts and do something? Okay, and hopefully we make some progress. So let's do the following. So I basically say this is f, which I break up into 3 roughly equal parts, and g, which also I break up into 3 roughly equal parts. So let me just write this as f0 plus f1 times x power d by 3 plus f2 times x power 2d by 3. And similarly, this is like g0 plus g1 times x power d by 3 plus g2 times x power 2d by 3. Okay. Sorry.
Oh, sorry. No, I just brain.
So all of f0, f1, f2, g0, g1, g2, they're all polynomials of degree at most d by 3.
Yeah.
Okay. And I want to compute the product of these 2 things. Last time we broke it up into 2. I'm just doing it with 3. That's it. So let's just ask ourselves, what are the terms that we want? If you multiply it out, this is what you end up getting. The multiplication of these 2 will give us f0, g0. Then if I want what is the coefficient of x power d by 3, that will be these cross terms. So that is f0 g1 plus f1 g0. And now I want what is the coefficient of x power 2d by 3. That will be a slightly uglier sequence. And x power 4d by 3, etc. So I mean, each of them will give you one such term of this form. So basically, if you did the naive multiplication of these 2 things, you will end up with 9 such terms. And you group them together and you put them at one shot. So there are totally 9 terms. Totally 9 products we want. I mean, sorry, or whatever. Okay, what I want to say is that we can do with 9 products and a few additions. Okay, like last time. I mean, the naive thing was you would get 4 products. I mean, if I compute those 4 products and do a bunch of additions, I get all the terms I am interested in. And now similarly, if I compute all of these 9 terms, this guy, this guy, this guy. Okay, if I compute all of them separately, then of course I can add up all these things and get what I want. But that will be no different from the high school method. Okay, and again, we want to do is, can we do with fewer? Like last time, instead of computing 4 products, we somehow managed to get away with computing 3 of them. So now instead of computing 9, can I get away with computing something substantially better than 9? Okay, and it turns out 5 is enough. Okay, there is a way of, just like we did in Karatsuba, just write down 5 different products such that all of the terms that you're interested in can be obtained using some weird linear combinations of this. Okay. So if we can do this, basically this will again give us another recursion. It will look like 5 times t of d by 9 plus an order d sort of thing, which we can solve. Okay, but let me tell you what the 5 terms are. Okay, and the 5 terms happen to be these. Okay, which on the face of it just seems bizarre. I mean, it's some bunch of 5 terms, which it turns out that actually these 5 terms are sufficient to do everything that's there on top. So certainly this is something that's already present here. Okay, so let me give you one such example, which is if you multiply equation 1 with minus 5 by 4, equation 2 with 2 by 3, this with 2 by 3, this with minus 1 by 24, this with minus 1 by 24, and add all of this up, you get basically f0 g2 plus f1 g1 plus f2 g0, which is one of the things. And basically all I'm saying is that all terms in, okay, let's give this a name. Let's just call this as star. Okay, star are linear combinations of these 5 terms. Okay. So, I mean, the thing is, what the hell is going on here, right? I mean, like how do you come up with something of this sort? Like, okay, so, and, but I'm hoping that, you know, some of you see some weird patterns in the terms that I have written down. Okay, can someone, is someone able to notice something? I mean, your guess of how one could come up with it?
Pascal's triangle, something. Pascal's triangle, something like that.
Is Ramprasad still on the call?
Pascal's triangle. Why? Sorry. So Pascal's triangle is basically the bunch of binomial coefficients or something, right?
Yes.
So yeah. So I mean, here doesn't look like binomial coefficients per se.
So one, I mean, I don't know what to think of the things that you're multiplying to get the final term, but at least in these products that we have, like all the coefficients are like plus minus powers of 2.
Okay. Okay. By the way, the following would have also worked. Like had I replaced this with 3 and 3 squared, and maybe replace this with, I don't know, 5 and 5 squared and stuff like that. Okay, maybe I shouldn't do this because then these coefficients are going to be different. Yeah, but yeah. But yeah, so therefore there seems to be some sort of pattern here. I mean, think of it as saying that this is where the squares here were put to 0. And these are the things where the powers were put to 1. These are things where powers are put to -1. This is like powers put to 2 and powers put to -2. On the face of it, it seems something a little weird.
We are evaluating these polynomials.
Exactly. Okay. So, and here is an observation that you must have seen in high school or wherever, is that a degree k polynomial is completely determined by k plus 1 distinct evaluations. Right. If you want to know a linear polynomial, if I tell you the value of this linear polynomial at 2 points, then you exactly know what the linear polynomial. There is only one. And if you want to know precisely what a quadratic is, then I need to just tell you 3 distinct evaluations, and that tells you exactly what the quadratic is. Okay. And
so
sorry.
basically, you are trying to we are here to do the polynomial multiplication. We are not representing the polynomials as a polynomials, but a points with the f0 and fx0, x0 and fx0, x1, fx1.
Exactly. Yeah.
R, comma Rn, and similarly for the G, and then we are doing the multiplication there, and we will do inverse Fourier to get it back, and I will see that this procedure.
Okay. At the moment, I don't know what Fourier is. I'm going to pretend I don't know what Fourier is, but yeah, but you are exactly on the right track. So that's what we are doing. So let me just slow down a little bit here, and yeah, but Saurabh, you're absolutely right. Okay. So the observation here is just that if you eventually want to compute some degree k polynomial, if you manage to figure out the value of this degree k polynomial at k+1 distinct points, then you can compute that polynomial. Basically, there's only one such polynomial. Okay, and this goes by various names. It's called Lagrange interpolation. Because that gives you a very explicit way of actually figuring out what the polynomial is based on these values. Okay, I don't know if, I mean, I guess people would have seen this in high school or somewhere. But in other words, I mean, here we will see a slightly different proof. I mean, which is, I mean, maybe not as explicit, but nevertheless, we'll see a different proof of this. So what I'm going to do is therefore the following. So suppose I have a polynomial h, which looks like h0 plus h1x plus h2x squared plus blah, 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 till hk x power k. Okay. Now let's ask ourselves, what do evaluations look like for the polynomial? So suppose I'm interested in what is the value at, I don't know, a point alpha naught. Okay, and maybe I'm interested in some other point alpha 1, etc. And I'm interested in the value at the point alpha k. If I think of this as a vector, okay, and I ask, what do I need to do if all I have are the coefficients? Because this is what is provided to me as input. And I'm hoping to compute these evaluations. Okay. And so computing it at alpha 0 is like you're just literally replacing x equals alpha 0. And that looks like some inner product, right? I mean, so I mean, you probably have seen this so many times. So let me just write this down. So it's going to be alpha 0 squared, alpha 0 per k, 1, alpha 1 squared, alpha 1 per k, etc. Okay, you just get this simple matrix vector multiplication. So that tells you if you have the coefficient, this is how you get the evaluation. Okay, which is called the van der Monde matrix. Okay, and the most important thing about the van der Monde matrix is that this is invertible if alpha i's are distinct. Okay, because the determinant is in fact exactly product of alpha I minus alpha j's over all pairs. Okay, I presume that you have encountered this in some course or somewhere. Okay, and I mean, if not, I will spend some time on this, but I guess you have seen this before. Okay, now that it is invertible, this basically says that if I know how to get the evaluations from the coefficients by this matrix multiplication, I can also do the reverse, because I can invert this matrix multiplication operation. Okay, so in other words, what I'm saying is that there exists some matrix, I don't know what this is, I'm just going to call this V inverse. Okay, where if I now multiply with h of alpha 0, blah, 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 till h of alpha k, this will actually give me the list of coefficients. Okay, there's nothing really fancy. You choose your favorite examples of alpha naught, alpha 1 till alpha k. This is some matrix that is made up of numbers. So when you invert it, this is also some other matrix that is made up of some numbers. Okay, and all I'm saying is that there is some matrix made up of numbers times your evaluations, which gives you the vector that you're interested in. Okay, this in general is called interpolation in general, which is that given sufficiently many evaluations, I can exactly figure out what the polynomial must be. Okay, and this process in general is called interpolation. Okay, so let me just write this as a thing that this is just to say that for any distinct alpha naught blah 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 till alpha k and any I which is in 0 till k, I know for a fact that there exists some constants. That constant is basically the ith row of this inverse matrix. Okay, there exists constants beta I naught till beta ik such that the ith coefficient equals the sum over beta ij. J goes from 0 to k of h of alpha j. That is, there is a way of taking linear combinations of these evaluations, okay, such that the ith coefficient, if you're interested in the ith coefficient, it's some suitable linear combination of them. And that linear combination is precisely whatever was the corresponding row of the matrix. If you want this, then it is this combination. If you want this, then it is this combination, etc., etc. And you don't particularly care about what the polynomial h is. Given alpha naught to alpha k, beta naught to beta k is, and the particular I, this is fixed. These are all numbers. Okay. So we just went to a digression, which was we wanted to originally multiply polynomials. And instead of multiplying polynomials, what we are instead trying to do at this point is basically saying that, oh, if someone gave me a bunch of evaluations, I am telling you that, oh, with these evaluations, I can put together the polynomial that I want. Okay, now what's that got to do with polynomial multiplication? So let's go back and ask ourselves, what did we want? We wrote down these two polynomials. Okay, for now, mentally think of, instead of having this x power whatever, let's put a y here and let's put a y squared here, where y is playing the role of x power d by 3, but let's just think of y as a formal variable. Okay, what are the terms that we are interested in? We basically said, let's multiply these two polynomials together. This is a quadratic polynomial in y. This is another quadratic polynomial in y. So when I multiply them together, I will get some degree 4 polynomial in y. The 5 terms that are there in the degree 4 polynomial are what is written here. So when we say we want to compute these 5 terms, a different way of stating this is just saying, I have a degree 4 polynomial I am interested in computing. Can you somehow cook up a way of figuring out what the coefficients of this degree 4 polynomial is? And what we are instead going to do is, like, instead of telling you what the coefficients are, I'm going to come up with a way to evaluate this degree 4 polynomial on 5 distinct points. Once we do that, we'll be able to figure these out. Okay, I'm just giving you the roadmap right now. We'll just follow it through at this point. So let me just define what is that? Sorry, let me call f tilde as f naught plus f1y plus f2y squared, and g tilde is g naught plus g1y plus g2y squared, and the h tilde I am interested in is basically f tilde g tilde. I want all the 5 coefficients of h tilde. Okay, so we want all 5 coefficients of h tilde, because those are the 5 terms that we were looking for. Is it okay so far? I hope until this point we're not doing anything fancy. Okay, and so now let's ask ourselves, okay, I wanted these 5 coefficients. How can I get these 5 coefficients? Okay, so what I'm going to do is I'm going to figure out, can I figure out what h tilde of 0 is, and say h tilde of 1 is, and h tilde of -1, h tilde of 2, and h tilde of minus 2. The reason it is 5 points is because I know for a fact h tilde is a degree 4 polynomial. So to completely figure that out, I need one more than its degree. So which is 5 points. Okay. What is h tilde of 0? Because h tilde is equal to f tilde g tilde, h tilde of 0 is nothing but f tilde evaluated at 0 times g tilde evaluated at 0, which is g naught h naught. What is h tilde of 1? That is f tilde evaluated at 1 times g tilde evaluated at 1. And that happens to be f naught plus f1 plus f2 into g naught plus g1 plus g2. And so on and so on. And that is precisely what we wrote here. If you just notice, this is the evaluation of f tilde g tilde at 0. This is the evaluation of f tilde g tilde at 1. This is the evaluation of that at minus 1. This is the evaluation of that at 2. And this is the evaluation of that at minus 2. There's nothing special about choosing 0, 1, 2, minus 2 or whatever. Just choose 5 distinct points that you like. Okay. And the interpolation thing basically says, once you know these are the 5 evaluations of the polynomial h you're interested in, every coefficient is some linear combination of these 5 evaluations. And that's why all of these terms are linear combinations of these terms. Okay. So basically, just to complete what we were doing here. So therefore, all terms in star are linear combinations of these terms. So the magical random sort of products that we wrote there, it's not with, I mean, there's some method to the madness. And we did this because what we wanted to do was, instead of figuring out the polynomial, we said, okay, can I come up with a way of figuring out the evaluations? And once you figure out the evaluation, there was a way to turn that around and figure out the polynomials. Okay, so was this okay? I mean, so basically, if you work out the time complexity, you will end up getting something like d power log 5 by log 3. Okay, so that's what you will end up with. So more generally, what you would want to do is this. Okay, which is you will take your polynomial f and g, split it into, I don't know, k plus 1 blocks or k blocks or something. Okay, that is, think of them as f tildes and g tildes. In Karatsuba, we had chosen it to be a degree 1 polynomial. In this, we chose it to be a degree 2 polynomial, but in general, you could choose it to be a degree k polynomial. That is, you have k plus 1 blocks. Okay, and then what you will do, you will basically say, okay, can I evaluate these k plus 1, whatever the product polynomial is, on k plus 1 distinct elements. So you will choose your favorite k, 2k plus 1 distinct elements, because when you take a product of those two, you now get a polynomial of degree 2k. So to completely figure that out, I need 2k plus 1 points. So you choose your favorite set of 2k plus 1 distinct points, and you compute all of these products. Okay, and compute the right linear combinations, and you get back whatever you wanted. So I hope this is clear. You will choose your favorite set of alpha naught to alpha k plus 1. That will tell you what this matrix is. It's a scalar matrix. It's made up of numbers. You know how to invert that scalar matrix. I'm just ignoring the fact that k is a constant, so all of this I can do on the side. And so I know exactly what linear combinations to take if I want to pull out a specific coefficient. And that's it. So that's the general algorithm. So what will the time complexity of this look like in general? So can someone say what recurrence we end up getting? So how many subproblems do I have? How many different multiplications do I need to compute? So
these
previous
2k,
huh?
sorry, the products that
Right. So these are all the products that are going to be my recursive calls. Right. That's what I'm going to recursively use the polynomial multiplication to compute all of them. So how many of them do I have?
2k plus 1.
So I have 2k plus 1 such terms. So it's 2k plus 1 recursive calls, but each recursive call is a call involving what degree polynomials. So in some sense, think of it as like saying this had d, this was a block of length d, which I broke up into k plus 1 chunks. So each chunk will end up being a block of length d by k plus 1. Right? So you get d by k plus 1. Plus, I now need to do a whole bunch of additions. Like even to compute a single such term, it seems to need about order d such additions or something like that. And in fact, if you just look at what happens, you will get order k times d. But think of k as some constant. Okay, just to instantiate things, if k was equal to 1, then you basically get 3 times t of d by 2 plus order d, which is Karatsuba. Okay, if k was equal to 2, then you get 5 times t of d by 3 plus order d. Okay, and if you compute what this is, you end up with, I don't know, some function of k. If k is a constant, you don't particularly care about this function, times this is going to look like d power log of 2k plus 1 divided by log of k plus. Okay, so is this okay so far? I mean, so okay, so this is basically c of k is some function of k. It might be an ugly function of k, but if k is a constant, this is some constant, so we can shove it into the order notation. But the important thing is the exponent starts looking like roughly something like log of 2k divided by log k. Okay, so the point is, if you mentally think of k being a very, 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 very large number, okay, this starts getting very, very close to 1. Because log of 2k is going to be log k plus 1. I mean, okay, and you're dividing, or log k plus whatever that log 2, depending on what base, and you're dividing by a log k essentially at the bottom. So as k becomes larger and larger and larger, this exponent is basically like 1 plus epsilon. Okay, this gets getting worse and worse as k becomes larger. Like for instance, one extreme case is if you choose k to be equal to something like d by 2. Okay, if you choose k to be equal to d by 2, then it feels like, oh, you're making amazing progress here, but this stupid term is already being the order d square. Okay, so it's stopping you from taking k to be too large, but nevertheless, if all you want is I want an algorithm that runs in time 1.1 d power 1.00001, then there is a suitable choice of k that will push that exponent less than that. So this in general, this was by Anatoly. Sorry, actually I don't know. Oh, sorry, Karatsuba. I don't think his first name is Anatoly. I think Toom is Anatoly, but and Steve Cook cleaned up. I mean, gave the modern exposition of Toom's algorithm is by Steve Cook, and this in general is called the Toom-Cook algorithm. And in general, it says that polynomial multiplication, you can do it in time d power 1 plus epsilon for any constant epsilon greater than 0 of your choice. Okay, and this is the rough outline. So are there any questions right now? So one of the things that sort of this seems to lead us to is that we started off by doing polynomial multiplication, and suddenly we went into these two potential sub problems, which is that I'm interested in a polynomial, I have a certain set of points. Can I compute the polynomial's evaluations on this set of points quickly? Okay, that could have been one sub problem that appears to be relevant if you want to speed up what we are doing right now. Another thing could be like, I tell you what the evaluations are, and you had to do this Lagrange interpolation type thing to figure out what the polynomial was. So far, we said all that is easy because k is a constant, so we can get away with those things. Okay, but those also might be interesting questions. So in general, let me just summarize. What did we do in the process? We wanted to compute a certain product f tilde g tilde. And we said if f tilde has degree k and g tilde has degree k, whatever this polynomial is, it's some polynomial of degree 2k. So to figure out that polynomial of degree 2k, I need 2k plus 1 evaluations. And in order to figure out those 2k plus 1 evaluations, I need to evaluate f tilde and g tilde at those points. And once I get those evaluations, multiply them together. So that would give us the sufficiently many evaluations to have complete access to h tilde, at least information theoretically. At this point, we only know that these evaluations completely determine h tilde.
Where did you add also the process? There is also the operations that you taken from to given a polynomial. You are going to the representation by n points in r comma rn rd.
Sorry, what do you mean by r comma rn or whatever?
I'm trying to say that so you are given two polynomials, not the representations, right?
No, by polynomials, I mean I'm given it as a list of coefficients.
Yes, I'm trying. Yeah, and from there you are going.
So from that list of coefficients, I can just break that list of coefficients into smaller sublists. Right? That's what my f0, f1, blah, blah, blah till fk are. Okay, and then I need to compute each of these whatever sums. That overall might take something like order kd. And then I multiply them. Those are recursive calls. And then I do the linear combination again based on the inverse of the van der Waals. That is another order kd. And so that's how it goes.
So basically for k degree polynomial, for d degree polynomial, we will do d plus 1 or like something like that, breaking parts.
No. So I'm always thinking of k as being some constant. Think of k as, I don't know, 4 or 5 or something like that. So we'll break it up into, I don't know, 5 or 6 parts. And we'll just keep on recursively doing that. I mean, the same thing that we did for Karatsuba's case. Karatsuba's case, we broke it up into 2 parts, which is like k equals 1. So it's a degree 1 polynomial in some sense. So you needed 2 evaluations. Sorry, you needed 3 evaluations because when you multiply them, you get, oh, is my voice a little?
Yeah, sometimes it's getting stuck.
Oh, okay. I don't quite know what the thing is.
It gets stuck and then it comes all together and falls forward.
Okay.
I thought it my internet issue.
No, I think it's probably mine or something. I think I'm connected to the network downstairs. So yeah. So this is basically what we do. So all the other operations like these additions and all, sorry, not this addition and this addition, it's an order D operation. And this particular multiplication and so on, I needed 3 multiplications of degree D by 2 polynomials. And the same sort of setup is there for the higher degree stuff. Okay, so this is the rough idea, which is that we basically reduced our question, which was on degree D polynomials, to computing some product of degree k polynomials where k was a constant. In Karatsuba's case, k was equal to 1. I mean, in the example that we saw for Toom's case, k was equal to 2. But in general, you can choose any k that you want. And we reduce the problem to computing f tilde g tilde because that will tell us, can I compute all of those terms by getting away with computing fewer products, fewer recursive calls? Okay, and that's what we did. So natural question to maybe ask is like, why don't we do this directly on fg? So eventually, can we take the following approach, which is that I'm eventually interested in computing the product fg. Okay, f was a degree D polynomial, g was a degree D polynomial, fg is a degree 2D polynomial. Okay, if I can evaluate the polynomial fg on 2D or 2D plus 1 different points quickly, then I can do more or less the same thing. oh, okay, I figured out what the product is, because in some sense I know what the evaluations are. And if I can do Lagrange interpolation very quickly, then I'll know what the coefficients are. Right? So this seems like something that we can try directly rather than splitting it up and pretending as if it's a linear polynomial and so on and doing stuff there. Okay. So general question is like, you could ask, maybe at this point, the choice of where you are evaluating your polynomial becomes important. Okay. Like you could say, are there a set of nice points? We don't even know what we are looking for at this level. Are there a set of nice points such that we can quickly evaluate a given polynomial on all of these points? Okay, so we are interested in polynomial multiplication, but somehow it naturally seems to lead us towards trying to come up with this multi-point evaluation system. Okay, so okay, and the answer to this is yes, and this is one of the most important algorithms in all of algorithms, which is called the fast Fourier transform. Okay, and that's going to be the focus of the next lecture. So intuitive. So I'll just summarize. I'll just state what things are, and then we'll fill in the blanks later on. I mean, this is like informal. Okay, if the set S is nice enough. Okay, and I'm thinking of the set S as consisting of something like 2D plus 1 elements, because that's what you might want. I mean, when you compute a product, if you want to know exactly what the product is, you might need 2D plus 1 points. Okay, then we can do this multi-point evaluation in time, okay, order d log d, okay, provided the space of coefficients is nice, whatever that means. Until this point, we were completely oblivious to where the coefficients were coming from. Okay, but as we will see in the FFT algorithm, it will turn out that if your coefficient space is nice enough, in the sense that, I mean, I'm going to drop a few things, which is like if there is what is called a root of unity of the right order present in your thing, then you can actually do like compute all of these evaluations in order d log d time. The naive thing seems to be like, if I just go one point at a time and figure out the evaluation on each such point, it seems to take d operations per point. So we'll end up taking something like d squared. And now it turns out you can actually do multi-point evaluation under this nice set of points in order d log d time. So that will basically say that I can do up till here, I can do in about order d log d time. And then comes the stupid headache of, okay, now that you have found these evaluations, how the hell do you figure out what the coefficients are from these evaluations? Okay, and surprisingly, that also happens to be only order d log d time. So the FFT algorithm will eventually tell us that polynomial multiplications over nice coefficient spaces can be done in order d log d time. And if the coefficient space is not nice, you can maybe add some additional factor of log d or log d and make it nice and then do it there. So basically we'll come up with a different way of, if all you wanted was this, you wanted to come up with an algorithm which was better than d power 1 plus epsilon for every epsilon greater than 0. FFT is the best thing that you could do. But the reason I didn't want to directly go to FFT is because directly going to this evaluation way of looking at these polynomial multiplications seems like it's too much of a jump. So if you see natural generalizations, then it's perhaps easier to convince you that it makes sense to study multi-point evaluations. Okay, so that's what we will do in the next lecture. Okay, we will do the fast Fourier transform. And this particular thing might be a stepping stone for many of other algorithms that we might end up seeing. Okay.
It is like a tree argument, right? As far as I remember.
I mean, it's something very simple. It's going to be a divide and conquer. I mean, we're going to try and break it up into sub problems. But now it was good early. Previously, it was like I wanted to multiply, so I broke it into sub problems. Here, it will be like I'm interested in evaluating a certain polynomial on a bunch of points. I will break that polynomial into two sub polynomials and ask, can I compute multi-point evaluation for this guy and this guy separately, and somehow combine them together. So it will look like a tree. I mean, but almost all recursive algorithms look like that. Yeah, it's a pretty clever algorithm. And I would have said that, maybe 10, 15 years back or something, FFT is probably the most run algorithm on general computers. But now it is probably just matrix vector multiplication or something. Yeah. Yeah. So, okay. So in the next class, we will see the fast Fourier transform algorithm. So, and that will complete the proof that you can do polynomial multiplication in order d log d time, and then we will start investigating the other questions. Okay, so I don't want to, I mean, we're stopping a little early, but this seems like a good point to stop. So I'll just take questions and we'll meet on Tuesday.
I think I should have known this before, but what is the best we can do for polynomial multiplication?
So order d log d.
The lower bound, like easy to say.
So that we don't know yet. I mean,
okay.
Yeah, we don't know if, I mean, it's widely believed that d log d is a lower bound for polynomial multiplication, but I mean, there are good reasons to believe that. I mean, but many of those reasons ended up crashing due to other things. I mean, somehow I think this is something that is very widely believed, that you can't do polynomial multiplication better than d log d. But we don't quite know that yet. In fact, until very recently, the best algorithm was, I think, d log d log log d, just because of the fact that you need your space of coefficients to be nice. And if it is not nice, you will have to do some massaging that loses an additional log log d factor or something. Okay, but not needing to even spend that log log d factor is something that happened very recently. Yeah, and yeah, but it's whether or not this is a lower bound is open.
Yeah. So one thing so all is order is depending on the field, right?
Yeah, at the moment, again, this is the number of field operations you need for this.
If the field changes, the order also will change, right? Means you are.
So I'm thinking of it as saying I am given a polynomial from a field S, and I am told that all arithmetic inside this field is unit time. Now, in the process, if you start coming up with a different field, a slightly larger field, and do operations there, I'm not going to count those as unit time operations. So one needs to be a little careful. I think this will become clear in the next lecture, because in order to make things nice, I might actually change the field. But then I can't just say that in this new field also it is a unit cost operation. Just like you said, if all I know is to multiply two real numbers,
the point is that if we do in zx, if we just do this unit time in zx, and z root 3 in the field z root 3 or something like that, it will take more time, right?
So again, so let's be precise about what do we mean by time. Let's instead say, how many operations on z do you need? That's what I'm going to count. The only thing I'm going to count is like, how many integers did you end up multiplying? I mean, if your underlying field is okay, z is not a field, but yeah,
q.
Yeah, let's say it's q. Then I'm only going to count how many rational numbers did you end up multiplying or adding. So in the process, if you decide to throw in a root 3 and do some operation there, the whatever the subroutine or library I have provided for you will only do rational number multiplication. So you decide to use the library in any way that you want. So that is up to you. Did that make sense? I mean,
yeah.
Yeah. So for example, if somebody gave you a real number library and you now want to multiply two complex numbers, the naive way of doing it requires 4 real number multiplications. But now that you have seen Karatsuba, you can get away with doing 3. If multiplication is a more expensive thing than addition, then there is a way of trading things off. But if both multiplications and additions are roughly the same cost, then it may not make sense. Okay, so, but these are going to become very relevant later on, because oftentimes what we might end up doing is like, we are working with a certain set of coefficients, and my coefficient space does not have the sort of property I want. So I might artificially expand my world of where these polynomials come from, because I want to use one of these, I don't know, whatever, e power 2 pi I by 3 or something like that. And for that, I might have to end up going to complex numbers. But I need to figure out a way of how can I do all those arithmetic given just the real number arithmetic. So that's going to be the slightly more involved part. Okay, so we'll deal with these nuances in the next lecture and the lecture after that. Okay, so if there are no, there seem to be some 2 chat messages which I missed. Okay, there is a mysterious sorcery message. I don't even know what context it came up.
I was like, how are we figuring out like that those coefficients, which later turned out to not be sorcery.
Okay. Okay, cool. So if there are no further questions, then let's meet on Tuesday.